And also there's a sign-up sheet because we're going to be sending you all a package of materials and asking for your opinion afterwards. So I'll pass that around if you just put your email and your name. That'd be great. So getting started, I'm Staudhammer. I'm from the University of Alabama, and I started out life as a forest biometrician. But now I'm in a general bio faculty, and I teach statistics courses for biologists. So today, of course, we're going to be talking about the importance of experimental design in ecological research. And why is it important? Well, everybody in this room, I'm sure, knows why it's important. The first step, of course, in making a rigorous test of your hypotheses is having the, planning how you get your data. And planning how you get your data so you get the kind of data that you need to support or refute your hypotheses. So regardless of whether you're doing an observational study or an experiment, the same kind of rules apply. And we need to make sure that the data collection methods are going to allow us to get the fruits of our labor. It's very it's hard to be in a situation where you look at the design and say, well, you can't really test what you want to test. So we think about planning. So we collect data with a purpose. That's what I always tell my students at Alabama. We need to think about independent variables for explanation, our response variable, that's what we want to make inference about, and of course that data follows with what hypotheses and questions we want to answer. And depending on the design, we have different levels of uncertainty. So the beginnings of experimental design were in the beginning of the 20th century with Ronald Fisher, of course. He's an interesting figure in statistics. And since his first book on experimental design, things have gotten a little bit more rigorous. I don't believe that he talked about the need for randomization in as much as we do now. But basically, the three main things that we need to have for making statistically defensible statements after we collect our data are randomization, replication, and some sort of design control. So why do we need randomization? Well, we're all biased. Unfortunately, humans lack the ability to pick out a representative sample. There are lots of interesting studies on that. And we want to have replication so that we can actually calculate a variance. We need uncertainty in order to test our hypotheses. And plus, we need insurance in case something goes wrong, right? So we want lots of replicates if we can. And we want to have design control, which means that we collect data in a way that we can use various tried and true methods. And for instance, we might need homogeneous experimental units for our particular test, or we might need to use blocking because we know we don't have homogeneous experimental units. So we'll talk a little bit more about each of those, and I'll try to make this fast so that we have enough time for the hands-on. So randomization, again, we need that for testing our hypotheses because our own biases always enter as much as we like to think they won't. So if you're studying plants, you need to have some sort of random mechanism for selecting them. If you're making measurements on fixed area of plots, you need to have some random mechanism for establishing where they are. Now I know that's so hard in our line of business, but we have to have some sort of random mechanism to have statistically defensible results. But, as ecologists, but there's always a but, if we don't, or we are not able to randomly select, we just narrow our inference space. Okay, so if we have to sample in a certain area, that's really our inference space, and making statements about the larger population are harder. And if you're doing an experiment, you need to think about, therefore, randomly allocating your treatments, whatever they happen to be, to those groups. Those experimental units are randomly allocated to the treatments. Okay, so replication. We need to have multiple units, like I said, to calculate variances. And that goes for every single combination of factors you might be studying. So, for instance, if you are studying two species, you need to have at least 4 observations, but that's pretty dangerous. I wouldn't recommend that. But if you do take more observations, you can certainly have uneven numbers of observations, unless they're very, very uneven. We want to have them kind of the same. So if we replicate, we also reduce the chances of having some sort of bias in our data, and also we reduce the effect of weird observations. We all know that 20th time we get something that's just wacko. Okay, if we have a lot of replication, we can even out that, and so our uncertainty estimates can be lower. And of course, if we have lower uncertainty, we can be more confident about attributing the differences we see to some sort of treatment effect or whatever it happens to be that we're studying. One thing that always comes up when we talk about replication is pseudo-replication. And today we are going to be talking about some designs that if we weren't careful with them would indeed have pseudo-replication. Biologists in particular have a difficult time with replicating the exact same conditions. You know, our two soil pits, even if they're a meter apart, they're going to be different. Are any two rivers the same? Absolutely not. But we call these things replicates, and very often they're pseudo-replicates. But we also have pseudo-replication in long-term data because we are very often measuring the same thing over and over again. So obviously, if you measure the same tree 2 years in a row, those observations are not independent. So we're going to spend quite a bit of time talking about that. But we also can have correlation between measurements that are taken close in space. And we're also going to talk about that as well. So independence is necessary for most of the tests that we have for sort of basic things, t-tests, for instance. But if we can't achieve that, we have ways of mitigating it. Here's an example I like to put up of are these really replicates? Let's say you have a burn and you pair some unburned plots with some burned plots. Are these really replicates? Well, if your scale is small, really no, it's not. But even if your scale is a little larger, are they really true replicates? There are lots of opinions about this, but if a fire was applied to just this one area, we really only have one replicate if you want to take a really hard line, even if this is hundreds of hectares. Some statisticians would say those are pseudo-replicates, you don't have an experiment. But what you can say is that if you can't have multiple fires, you can generalize to this fire. That's fine. You can make an inference about this fire. But if you want to generalize about fires in general, you need to go out and get more fires, have more burns. Okay, so experimental design is the way that we apply quote-unquote treatments, and often, of course, we're monitoring things. We're not applying treatments, but the same things apply. And how we select the data from the different populations of interest. So this is intimately related to how we analyze the data. I always ask my students to come in with a picture, because it really tells much more of the story. So the sampling design under which you collect the data controls how we're going to analyze it, just as the experimental design does. So here's a quick example. We want to describe, I do some work in longleaf pine savanna. Maybe many of you probably didn't know we had savannas in the US. We have that. We have a 90-hectare area where we have 3 different understory types, let's say, and they're 20 in shrub oak, 30 in wiregrass, and 40 in mixed grass and shrub. And we could even be in a couple of different situations. One situation could be that each of those understory types that in our study area covers some sort of contiguous area. Or we could be in the situation where we have a patchy understory. So in the first situation, we would be looking at a design. We could do something like this, as we love to put in grids as ecologists. It could be this, but it also could be this. And those things are analyzed differently. We have very different design and different uncertainty associated with those things. So we have to know what we're dealing with before we know how to analyze it.
Can I interrupt?
Sure.
The first one being considered pseudo-replicated by some very extreme statisticians.
Yes, if you were a hard-line statistician like some of my colleagues, you would say, yeah, that's not the pseudo-replication. But if you're talking about an area that is very, very large, you have a nested design, and you can get away with it. You always want to have a correlation structure for something that's like this. But yeah, this would be an example of a nested design if you have a large enough area. But your inference space is pretty limited. Okay. Another example, if you wanted, let's say we were interested in disease presence in frogs, and we have we want to tell how these frogs react to different moisture regimes. Say we have a low, a medium, and a high, and we have some space available in these blocks. And they could be aquarium, groups of aquarium. And we could do a couple of things. We could put 9 frogs in each block, or we could split them up, put 3 frogs in each of the 3 blocks. And we might be looking at a situation that either is this, or it's that, or it could be that. So depending on what your logistic constraints are, though, you might have to do that. And my advice is just sort of come clean about it, but a lot of people would say that's if you need to do it another time. Because you don't have, if you have, say these are spaces that are pretty different, if they're in different rooms or different areas, you would be in trouble with this because your replicates are very close together. This is more powerful, and this is even more powerful. The uncertainty for this kind of design is going to be less. Or, sorry, it's going to be more. No, it's less. Have a smaller conference table, sorry. So under different circumstances, you might be forced to get into each of those situations, and you have a different level of uncertainty. Okay, so as we get started on this, we'll talk about some of the assumptions that we make, of course. We love to assume that our populations are sort of normal. It doesn't always happen, but we like to assume that. If you have a very skewed population, you need to think about transforming that data. If you have a multimodal population, usually you need to be thinking about a non-parametric method. But note that the designs the tests are pretty robust to moderate assumptions. So even if you fail, say, the Levine test for homogeneity of variance, unless you fail it really terribly, you can probably get away with it. There have been some simulation studies that have shown that depending on the degree of skew, the tests are still valid. So there's some good publications in the last few years about that. So the other sort of nasty thing that we see in ecology is the homoscedasticity or equal variance assumption that I was talking about with the Levine's test. Often if we can transform the data, though, for number 1, we can fix that problem. But that's a very important assumption. But these 2 assumptions are important for testing. And third, of course, we have random selection, just like Fisher wanted us to. And the 4th thing is that the samples are independent. So if we don't have independence, we have to come clean, and we have to declare that in our models. We need to start thinking about adding random effects. So we're gonna go there. So we're gonna talk first about the very basic design that most of you, I'm sure, are familiar with, completely randomized design. And then also talk about randomized complete block designs and how they change our uncertainty estimates. I'm not going to have time for split plot today or any other designs, but there's lots of good information about those. But anytime you restrict randomization, you change the design and you change the uncertainty estimates. Okay. So a completely randomized design is a situation where we have experimental units where our treatments, or whatever they happen to be, are randomly allocated. And we have no restriction on randomization, meaning that when I get to a particular unit, I make a random selection. Doesn't matter if they're next to each other or not. Okay, so CRD is the simplest way that we can estimate a model. And these are general linear models, or they're also called ANOVAs, same thing. And they give us equivalent results. So in this case, if we had 3 treatments, 3, let's say, irrigation levels, we have 2 degrees of freedom, and we have our number of replicates minus 1 times the number of treatments for the degrees of freedom for the denominator. And that's a very important degree of freedom because it really helps us to have a sensitive test. If we can increase that number of replicates, we can make those degrees of freedom go up, and we can have a much more sensitive test. So anything that we can do to make that F statistic be larger is going to help us to support whatever work we're doing. I don't think there's anything else I want to say about that.
So as we have more experimental units, of course, we have more power, but we don't always get the luxury of having more experimental units. So we also have to think about, well, how can we increase this F-test? Maybe we can do something about this error. So we'll also talk about that. Okay. And unbalanced designs, as I said earlier, balanced designs are nice, but they're not necessary. As long as you don't have numbers of observations that are too different. You don't want to have 2 in one and 20 in another. As long as they're not too different, all the concepts are the same and they're very easy to estimate. So how do you fit a CRD in R? Well, this is the simplest thing that we will do today. We'll do this first just to make sure we're all on the same page with R. We'll fit a linear model and using LM. So LM can be used as long as you don't have any random effects in your model. So we have a fixed effects, which is after the tilde, and our response variable is what comes before the tilde. And if we want to do any sort of post-analysis, we have to tell R to put the result into an object. So I'm telling it to run the linear model and put that output into this object called lm.irr. Okay. I also tell it what data set to use. Then I have some more steps to do. If I want to have that nice analysis of variance table so I can see what's significant, I need to ask it for an ANOVA. And then if I want to know anything about the estimates of each of my irrigation means, then I have to ask it for a summary. So those are, at a minimum, the 3 things that you should do. But we cannot forget that we need to also see if we met the assumptions. So probably the most important thing we do is the 4th thing, which is to plot. Okay, so if you ask R to plot the object that you created, it'll give you a series of 4 plots that have lots of information about if you've met the assumptions or not. Although you could do formal tests as well. And finally, if we do want to know what the mean values are of our, for our different effect levels, we need to produce some marginal means. They're also called least squares means. They started out being called marginal means, and then SAS called them LS means, and so now everybody calls them LS means. And these are very, very important because when you do an experiment like this, and say you wanted to compare treatment levels, you get to use all of the data, even if you're interested in talking about the mean of one of your treatments. One of the most powerful things about analysis of variance is that when we assume that our variances are homogeneous, we get to use the experimental error variance for creating any confidence interval. So if we take all the data, we can be more certain about that estimate. So least squares means are going to be different from what you get from just getting the mean of your own data. If you have an unbalanced design in particular, you should really get in the habit of doing this, but also they give us confidence intervals that take that into account. So that's an important step. Another thing about R. If your if your categorical variable irrigation here, if I had numbered it, if I had said there were irrigation levels 1, 2, 3, but let's say they were different levels that weren't linear at all, and I didn't think the effect was linear, I need to make sure that R knows it's a factor. You have to be very careful about that, because if I had 1, 2, 3, 4, 5, it'll think that I'm going to fit a line. I'm going to fit that straight line relationship. So you have to be careful about how you do that. Okay, so here's some sample output, and we'll go through what all of these things mean. First of all, we have our analysis variance table. It's always good to check the degrees of freedom and make sure that we have estimated, what we think we've estimated. So we have our k minus 1 and our n times k times n minus 1 for the residuals. And what does it all mean? Well, it depends on your level of sensitivity, but probably you'd think this was a significant result, even though there's nothing magic about 0.05 or 0.01. People love to use those cutoff points, though. Here's the summary, and the summary does give us additional information about the spread of our residuals. One thing about the residuals is that they always will have a mean of 0 for this kind of model. So the median should be around 0, should be close. And it's nice to see that they're between, a good amount. This is biomass data, so in this case, you have to think to yourself, does this make sense to me that it should be off between plus or minus 3? And depending on your study system, that could mean something. So the other thing to note about the estimates is that R is giving you an intercept and then irrigation B and C. So I have levels A, B, and C. So this estimate is for my level A. It's always going to go in alphabetical order unless you tell it differently. And so this is the mean, actually, of my irrigation A. This 12, this estimate for B, is not the mean of B. The mean of B is going to be 2 plus 12. And mean of C will be 2 plus about 18. So it's giving you the sequential additional bump that you would get from using those different irrigation regimes. And these p-values over here are also important to note. If we go backwards, actually, let me go backwards one. Oops, sorry. So we had a very significant result there. And if we look at these estimates here, we see that there are very significant p-values here. These p-values are testing versus the base, okay? And they're two tests that are assumed independent, so really we shouldn't really interpret these with too much, without going to the least squares means. So you can interpret them in the sense that they're significantly different from the intercept, but they have to be two independent tests to really rely on those p-values. The other thing that LM is going to give us is a R squared. And people love R squared. And R squared is great for a linear model that has no random effects. Once we start adding random effects, the definition of R squared is very debatable. I know some journals, I've been asked on papers to put an R squared in for a mixed model. It's not clear what variation you're explaining. So there is no R squared printed out when you get to a mixed model for a reason. It is because it's not clear what it's explaining. Okay. And here finally we have our check on the residuals. Now, the residuals do look a little bit funny. They're all in lines, and that's only because we only have 3 possible predictions. We have 3 levels of irrigation. We don't have any other effects. They're gonna line up like that. And we also have a QQ plot. If we had data that was not very normal, we would not see that it lined up on that line. The QQ plot is very good to eyeball that normality assumption, and really I would put more stress on looking at this thing than doing a normal test. The normal test is very, very, very sensitive, and particularly if you have a lot of observations. You're always going to fail it. So I would put more credence in looking at the QQ plot. Okay. Now finally, these least squares means. Okay. So if you ask for least squares means, you can also ask it for pairwise tests. And by default, it's giving you a Tukey adjustment, meaning that it's keeping the family-wise error conserved. That means that it's adjusting for the fact that it's doing 3 tests. Okay, so if we do independent tests, we're talking more about what's on the other page. Normally, we want to test all of these things. So we have the means as well as their standard errors, and we can, of course, go on and make nice plots with those things as well. So we might want to also think about, what does this mean? Okay, so for irrigation A, my mean is 2, and I goes all the way down to -1. Now, if you're talking about biomass, it's probably not something you want to communicate. What do you do with that? Well, you could think about fitting a different kind of model, but for me, I would just say, well, I know it's less than 5.47 with 95% confidence, and probably wouldn't let it bother me too much more. Okay. And these p-values down here are with the Tukey adjustment, and it tells us that we have highly significant differences with A versus B and C, and not highly significant, but still fairly good difference between B and C. Okay. So now let's get complicated, because we are studying long-term systems. We don't take one measurement and stop, right? Okay, so what if we do go out and take multiple measurements? Or, well, actually I have them out of order. I'm talking about multiple measurements in the same spot. Forgive me. But in many situations, we collect data that is very closely together in space. it's just something that we do. My background is that I came through a forestry program, so we like to put in a fixed area plot and we measure all the trees that are in a certain area. It's convenient. It's really hard to go out and measure random trees. It's easier to go to this random spot and measure everything. So if we're in 3 sites and we measured 15 plots that each had 4 trees, we might have something that looks like this. We have a couple of sites, and on our sites we've got, different numbers of trees. Can I just throw that into a CRD? Probably should not. The other situation that we find ourselves in a lot is that we collect data on the same thing over and over again. Okay, that's why we're all here, because we do that. So for instance, we might be in 3 sites and we're measuring 15 trees at 4 different time periods. So how do we adjust for the fact that these observations are probably highly correlated? If I go back to the same tree year after year after year, those are not independent measurements. I'm more likely to find similarity between this tree and in year 1 and, going this way. These 2 measurements are probably more similar than these 2, depending on what you're studying. So I have a correlation structure that I need to think about. So if we measure repeatedly over time or on the same plots, we probably don't have independence, although there are tests for that. And if we don't have independence, we have broken this assumption. We are not meeting that independence assumption. And this is something that happens all the time in ecology and every other discipline as well. And of course, if we don't take care of it, we're talking about pseudo-replication, which is one of the big sins. So we need to appropriately analyze this by considering additional non-fixed effects. So far we just talked about that irrigation is a fixed effect. Now we're talking about random effects. So we want to develop models that account for that correlation, but there's also a secondary benefit. Oh, well, pardon me, sorry. So we want to make sure that we have the correlations on the data coming from the same plot. They need to be accounted for, and for repeated times, we want to make sure that the data coming from the same tree are taken as correlated. If we ignore those interrelationships, what's going to happen? Well, we will still have a fine measure of the mean. It doesn't affect the mean. We can make a very good estimate of the mean value. No problem there. But what's going to happen is that we're going to have artificially high degrees of freedom. So we have, tons of power, and our standard errors are going to be deflated. So we need to make sure that we are not pretending to have less uncertainty than we actually have. So if we have multiple measurements per experimental unit, we can find out those correlations and also use them to help us understand the system. Do we actually have correlations over time that are significant, or are they not correlated? And that does happen. Okay, so here's the example of a mixed model for multiple measurements per experimental unit. That is, I'm talking about the fixed area plots. I have 3 sites, and let's say I have 15 plots, and I am measuring, let's say, 4 trees per plot. How does that change our design? Well, we have, still for the numerator degrees of freedom, we're going to have just number of sites minus 1. But now we've added an additional error term. Our experimental error is the number of plots times, the number of plots minus 1 times the number of treatments. And that is the error that we want to use to test this for site differences. If we have correlated observations, that's the conservative thing to do, and it accounts for the fact that we have this 42 degrees of freedom instead of the 135. The other situation, of course, that we are often in this line of business is that we are measuring the same thing repeatedly over time. And what happens with that? Well, here we've got the same thing. We've got 15 trees. We're assuming our trees are independent here, which might not be a good assumption, but we're going to assume they So we have two sources of error, but we have several different tests that we get to make. Usually we're interested in time. Time is something that we want to quantify in terms of its effect on what we're doing. So we think about having two different sources of two different sizes of experimental unit, if you will. We have the sites that have 42 degrees of freedom because we have 3 sites and 15 experimental units. But the times have a different error to be tested against. The times are going to, well, and their interaction, which can also be important, get to be tested versus this within tree error. So the experimental error, you can think about that as being sort of a plot level area. Excuse me, a tree level error between trees, and this is going to be within the tree. So those times within the tree. The interaction is also important to look at, and I'm going to actually spend a little bit more time talking about interactions because sometimes we don't do a good job of interpreting them. So this is a case of 4 sites, 4 measurements per 15 trees, and we can think about each tree as being the subject that we're measuring. And that's a notation that gets used in some other programming languages, not R. But if you go and use SAS or SPSS, you will find that the subject notation is going to help you to figure out how to structure those errors. Okay. So the important thing about this is that we test the site versus a experimental error, and we test the time and its interaction with that within tree error. Okay. But this assumes that our times are actually independent of each other. And we're not really sure that that's going to be true. I mean, if we measure something over and over again, at time 1 versus time 2, those things, or time 2 versus 3, or 3 versus 4, adjacent observations are probably going to be more correlated than those that are far apart. Unless, of course, we have some disturbance that comes in. But we can probably make that assumption with some systems that observations that are closer together might be more correlated. So we need to think about first how our data are clustered, what are our subjects, what are the things that are possibly going to be related. And we need to think about the fact that our observations and their residuals are going to be correlated, not independent. So there are 2 ways to deal with this. If you are a SAS user like myself, I started out life as a SAS user, so I still love it. In SAS and some other programs like SPSS, we think about actually a marginal model or a population averaged approach. And then if you're an R user, you will probably be using a mixed model approach. So we're gonna go with that, the latter, but I'll explain what the marginal model is. So with the marginal model, pardon me, we don't model the correlation among the residuals. We actually model the covariance structure. So it's a little bit different than in the mixed model approach. In the linear model, we assume that those observations are independent. In the marginal model, we assume that the residuals from each subject are actually going to be related. Okay. And the covariance is assumed to be non-zero. It's not actually truly a mixed model. I did not realize this until recently. It's not actually technically a mixed model, but the mixed modeling methods are used to do that. So if you are a SAS user or SPSS user, these are the models that are modeled with a repeated statement. So they're a little bit different from each other. What we're going to be looking at today is the mixed model approach. And what we do is we control for the subject. We declare that the subject is a factor in our model, but it's not a fixed effect. It's a random effect. We redefine our residuals such that they're the distance between our observed values and the mean of that particular subject. And this has the effect of using less degrees of freedom. So what is a fixed effect versus a random effect? Well, fixed effects, when we study them, we are interested in making inference about those particular levels. We're not interested in making inference about some, other thing in the world. And we model it as a constant that doesn't vary. And if we repeated that study, we would be likely to choose those things again. That's kind of how we define a fixed effect. And regression models are a perfect example of this. If we make just a straight regression model, our x's are assumed fixed. And most effects where we go out and purposely measure them, they're going to be fixed. On the other hand, random effects are from a distribution. They are a sample of possible levels that we might be interested in. So, pardon me, this arises oftentimes when we subsample, when we repeatedly measure over time. Those things are going to be random effects.
I'm sorry, could you explain what you mean by levels?
Levels. Let's say that your 3 levels of irrigation. Those are the levels of your factor levels. Okay. So if it's a situation where if we were to repeat the study and we might choose different levels of that particular effect, that would also be considered random. So if we have some plot on the ground that we did our study on this time, and if we went and did it again, maybe we'd be over some other place, that's probably a random effect. You don't want to make inference to it, in other words. So how do we fit this model with the subsamples? We'll go back to this example where we have 3 site qualities. We have 4 trees in each of 15 plots, so we're talking about 60 observations in total. One of the most important things we can do is declare some factors. Sometimes we get into trouble with things that are numeric, that are used in the model and don't actually represent a quantitative term. So I always get in the habit of doing that. And this function that we're using now is in the package NLME, nonlinear mixed effects. There's a very, very similar structure to this function versus the LM function, but the important part is that we have this random statement. And this random statement looks a little funny. It has a equals tilde1 and then the bar, and then the random effect, which is, in this case, we have observations trees that are grouped in plots. So, oopsie. What that one slash, it's not really a slash, bar plot does is it fits a model that has random intercepts for each plot. Okay, so you can imagine, if you're thinking about this, you're losing a degree of freedom every time you put a plot in there, okay? Because it's fitting an individual intercept for each one. Then when we finish running it, we also, of course, want to still get our ANOVA, get our summary, and plot some residuals and make sure we're following the assumptions. Okay. One other thing. Okay, so I learned this the hard way in my adventures in ecology. So a lot of times we go out and we have several sites. We might have plot 1, 2, 3, 4 over here, and have plot 1, 2, 3, 4 over here. R does not like that. Don't do that. Renumber your plots. Have 1, 2, 3, 4 over here, and 5, 6, 7, 8 over there. I have gone through many ordeals with finding that to be an issue. It will not give you the right degrees of freedom. It will think those plots are related to each other. Be careful. Okay. So here's some output. The ANOVA looks a little bit different from, it doesn't give us the sums of squares, mean squares like the other one does, but gives us pretty much the same information. Always good to check the degrees of freedom, make sure we've done the model right. So the site quality will have 42 degrees of freedom, and that's what we want. That's the denominator degrees of freedom. The other thing that we're going to get out of the summary is some measures of fit, like the AIC, Akeki Information Criteria. I'm sure everyone who reads ecology journals has heard of it. Lower is better. So even if it's negative, you want it to be more negative if it's going to be a better model. So if we're going to be comparing models, we do want to take a look at the AIC. The other things that it gives us are estimates of the variance components. So we have fit 2 kinds of measures of uncertainty in that model. We have the residual uncertainty, and we have the uncertainty having to do with our within plot excuse me. That's the wrong page. That's within plot. That's between plot. Okay, so this is for our experimental error essentially, and this is for our subsampling error. So it's good to take a look at these things because it's telling me that I really have a lot more variability between my trees than I actually have in my plot. And that can happen if you have plot trees that are you know, and if it's a natural regeneration, you have different ages, you can have that happen. And of course we have the fixed effects estimates, and the tests are again versus the base. So you can end up here, and this is something that can also happen. You see that site quality has a p-value of 0.015, and you go down here and you say, oh, but nothing's significant. Okay, these are different kinds of tests. They're testing versus the base value. This test is whether this is 0. So is the base effect different from 0? And that might not be something of interest. And this is B different from A, and this is C different from A. And you can have p-values here that are non-significant and have one that's significant up there. Okay, because these are not testing what you think they're testing. The other thing that we do get are some correlations. These correlations, I don't pay too much attention to them. Some people look to these correlations to see if we have multicollinearity, but it's not a definite indication of multicollinearity, meaning that your X variables are correlated. What this means is that if you were to do the experiment N and site quality B, the estimate went up, that of C would go down. That's what the negative correlation is meaning. Okay, and then of course we have residuals. Okay, so here are our residuals, and again they're going to be in these nice 3 lines because we only have 3 levels of an effect to deal with today. Okay, now about the time. So we're about to start doing some hands-on. That's good. I'm talking too long. With this, we of course are using NLME again. We are very careful, very, very careful to make sure that time is a factor. Time is numbered 1, 2, 3, 4, but we don't have, a priori, we don't have a reason to think that it should go up or go down. We think that it might go in a nonlinear fashion. We need to make sure that's a factor. So we have that, and then we are running a model. The model is biomass as a function of site asterisk time. Now what that is a shortcut for putting in site time and site times time. So if you're a SAS user, you would think that was the interaction only. If you're an R user, this is the interaction of site times time. So the random effect looks very much like our previous random effect. We have random intercepts for every single tree. And here's some output. So again, we have the 42 degrees of freedom for our site, and we have a higher degrees of freedom for time and its interaction. Looking at the summary, if we had some competing models, we might take note of the AIC, but on its own, the AIC doesn't mean very much. And we have our fixed effects estimates. So here we have the situation where we've got some significant effects for site and time, but the interaction is not significant, meaning that we have the same kind of trend over time, regardless of what site we're in. Okay. The other thing to take note of here is our estimates of variability. Again, these are the 2 variance components that we had in our previous ANOVA table. And here we see that we do have more variability among trees than we do along times. So the measurements coming from the same tree are similar. Okay, and the same thing with our correlations. These correlation matrices will always look like they usually have a pattern to them. So. And here's our, of course, always want to make sure we test our assumptions. So look at the residuals. And by the way, if you do ask for a plot of the linear model from a mixed effect model, you won't get 4, you'll just get the 1. If you want a QQ plot, you have to generate that yourself, which is possible. Oh, I lied. We have a few more slides before the exercise. Okay, so are random intercepts enough? Okay, so when we fit this random intercept, we're saying every single tree had a different level. And we were measuring the variability around of the measurements over time for that particular tree. But what if we think that there might be different trends across time for each tree? So we fit a random intercepts model, but we could have fit a random slopes model, in which case we would say that our slopes varied by tree. Okay? And if it's a random slopes model, we assume that the intercepts are fixed. But usually people don't fit a random slopes model. They usually fit the intercept model, or they add the slope in there. That's what I've seen most commonly. So you are allowed to have both a random slope and a random intercept. And of course, it's more complicated. A lot of times it doesn't converge. So don't be surprised if you try to fit one of those and you don't get convergence even with a small data set, because it's a lot of parameters to fit. Think about how many parameters you fit. A lot. Okay, so if we fit that, we're saying that the patterns over time differ. So how do we do that? Well, we go back to our random effect, and we, instead of having a 1 there, the 1 indicates an intercept. If we replace that with our time variable, we will get a random slope as well. Okay, and so here is our output, and you will notice that with the random intercept only, we get similar, well, okay, we get the same denominator degrees of freedom, definitely. But our F values are actually quite different. And that's because we have a different experimental error when we do that. Our experimental error is being estimated with different components. We can also, at this point, now we have a competing model. We can think about using the AIC. So the AIC for this model is a 1,174. For our previous model, it was 1,172. So a little bit of a change. It's a little better to stay with the random intercept only. So if it goes up, we generally don't want to take it, especially since it's estimating so many parameters. And you'll find that your estimates of these coefficients are exactly the same, but the thing that has changed is our estimate of the uncertainty. The uncertainty estimates are quite different when we do that. And I don't have on here whether they're lower or higher. I suspect that they're lower. Okay. So one last thing before we have our exercise, because this is an important point. What correlation pattern, though, do we expect to see among observations that are taken on the same subject, the same thing over and over again? We assumed that our observations were equally correlated regardless of what time they're coming from. But we might have reason to believe something else. What if we think that measurements taken closer together in time are more correlated? Well, we have to consider dealing with this. Sorry. It's kind of frightening when you first look at this. But this is actually not so bad. This is the variance-covariance matrix. And these diagonal elements, the ones that have the same number for their subscripts, those are the variances among observations for different subjects at the same time. Okay, so this is essentially my variance, and well, I'll get to, I won't say that right now. The off-diagonal elements are the covariances between observations that are taken at different times. So when we make a model with assuming a dependence, so if we just did an LM instead of an LME, we are assuming this. We're assuming that we have homoscedasticity, so we have equal variance among all the times, and we're assuming that we don't have any correlation whatsoever between observations that are taken at different times. So we have a very, very simple situation. Now, if we don't tell R any different, we're going to get a compound symmetric matrix. R is assuming that we have the same variance homoscedasticity assumption, so we have the same variance for all the observations taken at different time points. And we have equal correlation between the different time points. So time 1 and 4 are as correlated as time 1 and 2. The other situation we might be in, though, is that we might be in this a situation where we think that observations that are closer together have more correlation. So here we say that observations that are one time unit apart are correlated as rho. If we go 2 time units apart, it's rho squared, and so on. and rho is between -1 and +1. So how do we do that with an AR1 structure? Well, we add another little bit to our LME call. We say correlation is equal to core AR1 up here. Actually, that's not showing up. And you will see that you get, you get pretty much exactly the same estimates, but again, our uncertainty estimates are going to be different. So the important thing that most people are going to be looking at, though, is the EIC. Did we do better by including that correlation? Well, our previous AIC was 1172, so we didn't really do that much better. And we can see if we look down at our estimate of, well, they actually call it phi. I don't know anyone who calls it phi, but they call it phi. Our estimate of phi is pretty close to 0. Yes?
Sorry to interrupt you.
No.
The AR1 is a set model within R, like
It's a variance covariance matrix that you declare.
Preset.
Well, okay, you tell it to estimate the row parameter, the off diagonal, but it's preset in there. So it'll estimate what row should be, and it'll estimate what the variance is. You can also tell it to use a certain row, but I'm not sure why you do that.
What was high, we should consider using the AR1.
Oh yes, absolutely. So if it's very high, or very negative, or very positive, so because you can have negative autocorrelation. I would suspect that they tested, if there was a test for this, I would suspect that that's not different from 0. So we pretty much have a compound symmetric structure. Anyway, so we have slight negative autocorrelation. Okay. And then we will have slightly different standard errors, but the estimates are all the same. Yeah. And why would you make it a continuous variable? Or
It's not a continuous variable.
no, it's not continuous.
Why would you just make it a continuous variable?
Well, if you believe that there was a linear effect of time, if you thought biomass was increasing in a linear effect, linearly, then you should, because you'll get more degrees of freedom, and you'll get a nice equation. But if you believe that it's not, that it varies, yeah, it just depends on your system. Yeah. So at this point, we could try other kinds of correlation matrices. There's a dozen of them, and but the AR1 and the CS are probably the most popular, and that's why I've discussed them. The other thing, before we leave this and have the interactive, literally 3 more slides to go, is that we need to also think about the interaction. So as we go through and do this exercise, we will be seeing some significant interactions between time and another variable. And when you have a significant interaction, if you have 2 factors, let's say A and B, it means that the effect of A depends on B. The effect of B depends on where you are in A. So if we have our 3 sites and we have time, we could be in a situation where neither site nor time were significant on their own, but they could have significant interaction. So we could be seeing this and say, didn't matter. Site didn't have effect, time didn't have effect. But what these graphs are hiding is the interactive effect. So we could have this situation where site isn't significant, time isn't significant, but we do actually have a significant interaction. If there's no interaction, if we do a graph of the sites by time, we will see that we have this parallel effect. But we could also, and I want you to watch this black line because this is the average, we could also be in this situation and have the same exact average. This is the same pattern, but look what we have. We do have an effective site, we do have an effective time, but they depend on where the other effect is. So it's very, very important. If you do have an interactive effect, you don't go on and that's the first thing you do is investigate what this looks like. If it looks like this is a significant interaction. You can go ahead and interpret your underlying effects just fine, but if you're in that other situation, you really need to be careful. Okay, so we have some graphical things that we can do with that, and on the hands-on exercise, there are some, at the bottom, there's some hints on the coding. So we can get started on that. And
Do you have the exercise?
yeah, there's 2 pen drives. Now, if you didn't get a chance to get the R packages, they are on there, but I'm not sure about the dependencies. I didn't download the dependencies. So, yeah, we'll see. But NLME is the most important one to have. So we're going to actually go through questions 1 and 2, and then 5 and 6. We're going out of order. The Word document and the 6 data files. So,
not the Staudhammer file.
No. You don't want all the methane data, do you? Okay, so. So if anyone has any trouble getting the data read in, just give me a holler. Because sometimes it can be tricky. Here's an example of how I get the data read in. I give it a working directory, and then I read it in from that working directory. I just find it is less typing.
Sure. Yeah.